Now, I am going to teach this with the assumption that you learned it last year. Though you learned it in May, you were probably on your last legs and a little tired. But you should have seen this material. Should be reviewed. Alright? Right. So, here we go. Thank you. Thank you. Okay. So let's start with the old parabola. So beyond the basics of how to graph a parabola, you also learn these little tiny super points about the focus and the directrix. Now, just so we're clear, if where a parabola comes from is this idea here. Imagine you have a point in a line. You with me? All right, cool. Now, if I said, give me all the points that are the exact same distance from that point as they are to the line, then there could be a lot of points the exact same distance. The easiest one would be to find right in there. Don't you agree that that's the obvious one? This distance here and this distance here are the same, yeah? If I go off to the side, I couldn't go just straight horizontally because now this distance is the same, but this distance is much greater. If I'm supposed to be getting points that are the same distance from the point in the line, then as I go off to the side, wouldn't I need to kind of curl up a little so this distance and this distance are the same? That should be maybe even a little higher. Are you with me? And if I went way out here, then it would be more like way up there. That this distance and this distance are the same. So the collection of all those points that are the same distance is what makes a parabola. Right? Now, the directrix, as far as I can remember, has very little value. The directrix is the line in the equation of the baseline kind of thing. The focus, though, is super duper important for physics. How is it useful in physics? Do you remember? Did you learn this at all last year? Okay, so one is collecting sound. Think of it as collecting versus sending out. If you were trying to catch waves here, then think of trying to catch waves from space. Well, this little tiny receptor is not going to get a lot of signal action because it's just one little point in space. Instead, we put it in a dish and we curve it so that as every single signal comes down, it gets bounced perfectly towards that single point. And so instead of just receiving one kind of signal from space, we get tons of different signals from a wide area all sent to that same point. The key is, though, that that point has got to be in the correct place. If I put my receiver here, but all the signals are being bounced there, then I miss and I get no signals. So that point has to be just at the right place to receive all those bounced signals. Are you with me? Okay? Likewise, if I have a flashlight. If I put that flashlight just up in space, then the light is in every direction, right? Okay. But if I put that light in a parabola-shaped dome, then not only is the light sent this way, obviously still, but the light that was being sent the opposite direction now is rechanneled to send back out, and you improve the lumens of the light. You with me? So parabola has lots of real-life applications. And the focus is what it's all about. The focus, in order to direct the light correctly, or receive the signals correctly, has to be just at the right point. So finding the focus is a matter of national security. Are you ready now? Now are you motivated? Sure, whatever. Okay, so the idea here is, first of all, the distance from the focus to the vertex is P. We typically just abbreviate that as P. I don't know if P stands for, honestly, don't ask. That P should be the same as the distance on the other side. should be equal to the distance from the vertex to the directrix. Now there is a bit of a relationship between P and the parabola shape. The distance P relates to the parabola shape. If a parabola is really wide, then those signals are going to get bounced really high. If you think about where that signal is going to get bounced to, it'll be way up here, yeah? So if the parabola is wide, then P is big, or the distance to the focus is really high up there. You follow? Are you with me? Okay. Likewise, if you have a really narrow parabola, then if I send a signal this way, then it's going to get bounced that way. Imagine how that, like if it was a pool ball, where it would be bounced. Well, if it's a narrow parabola, then P, here's P, the distance from the bottom of the parabola to that focus, P is small. Now that's where that's coming from. Don't we talk about the width of a parabola by saying, what's the A, the stretch factor in front of the parabola, right? The 2x squared makes it narrow, 1/2 x squared makes it flat. So it makes sense that this, the coefficient that makes the parabola, first of all, open up or down, and wide or narrow, relates to P. Okay? And would you write that either A equals 1 over 4P, or P equals 1 over 4A? That's just a bunch of symbol pushing right now, but I'll show you how we're going to use that in a second. All right, A represents the coefficient. A is the coefficient. Coefficient. Feel so sorry for you trying to read my hand. Okay, but I've seen worse, honestly. Let's go with a problem or two. So a parabola has a vertex at -2, 1, and a focus at -2, -1. Given those two little facts, that should be enough for you to write the equation of the parabola. Now I'm visual. Some people, I'm still baffled by how people can do this, but some people can do this without drawing a picture, but I'm not one of them. I got to see this a little bit. So the vertex is at -2, 1, and the focus is at -2, -1. That's down here. So I've got these 2 points. And just from that two little things, I'm supposed to be able to write the equation. How? Well, let's go with, first of all, the focus. The focus is always inside the parabola. So in terms of how this opens, it's got to open down for that focus at -2, -1 to be inside the parabola. So right away I know it's reflected down a -x squared. You with me? Okay, cool. Now, let's find P. P is what? 2. How'd you get that? Yeah, it's the distance between the two. P is the distance between them. And so in this case, P is 2. We went 2 units to get from the vertex down to the focus. You follow? All right. Now, let's write the equation of the parabola then. Y equals, cool. Let's do the shift part first. Normally, this is at the origin, and we shifted it left and up. So how do we shift it left to? plus 2 inside with the x, yeah? Squared. And how do we shift it? Up 1. Plus 1. We're all good? All right. Now let's talk the coefficient. The coefficient, first and foremost, it's reflected down, so I've got to have what sign there? A negative. And then what about the number? Well, that's where that idea comes from. The coefficient is 1 over 4p. In this case, we said the p is 2. So that coefficient must have been a pretty wide making factor of negative 1/8. You follow? Okay. And as for a couple other things here, write the equation of the parabola. Done. The directrix. The directrix is that line outside the parabola. And so in this case, where would the directrix be? Will it be above or below the vertex? Above, okay. How many units above? 2. Is the directrix a point or the equation of a line? Equation of a line. What makes a horizontal line? X equals a constant or y equals a constant? Y is constant. Y is always the same. So the directrix is at y equals 3. The same p distance that was the same p equal to above the vertex is how we got to it. Okay? The axis of symmetry, that's the fold line. If you were to look at a parabola, it has symmetry through the vertex. So the axis of symmetry is a mirror for the parabola. Where's the mirror for the parabola? So it's definitely at an x of negative 2, and is a vertical line x equals a constant or y equals a constant? X equals a constant. The axis of symmetry is x equals negative 2. Please, I beg you, these are equations of lines. So when I say give me the directrix, don't say it's 3. That's not an equation of anything. There's no equation there. It's y equals 3. When I say the axis of symmetry, it's not negative 2. It's x equals negative 2. You follow? Yeah, we kind of have a sketch already. It's pretty wide. My sketch isn't awesome. It's not bad. You follow? Questions?
How do you get the 1/8?
1/8. Good question. The relationship of the coefficient, so the coefficient, rather than write this stuff, a equals 1 over 4p, which is just a bunch of meaningless letters, let's write it in words. The coefficient that stretches the parabola is 1 over 4 times the distance from the vertex to the focus. Okay? Now we said, based on what they told us, we were able to decide that the difference between the vertex and the focus was 2 units, because we went 2 units down, right? So I was saying then that the distance to the focus is 2 units. In the formula, that's where 1/8 came from. Okay, and we're cool where the negative came from? Okay. This might be more meaningful than just a bunch of letter stuff. Okay. Let's go to B. 2, rather. Determine the coordinates of the focus for this here parabola. Okay. So I don't know if we need a picture, but what would the graph look like if I had to? It didn't say you had to, but what does the graph look like? It's a parabola that's really wide or really narrow? Really wide. I'm talking really wide. And at the origin or shifted? At the origin, okay. All right, so it's some really wide parabola, which tells me that when these signals are bounced up, that the focus must be way high up there, because wide parabolas tend to send signals way high up. All right? So we talked this up there. I said, hey, memorize this stuff. P equals 1 over 4a, and all that, which was obviously meaningless. So instead, let's talk about what this means. The distance from the vertex to the focus is 1 over 4 times the coefficient of the x squared, all right? So in this case, the distance that I need to travel to the focus is 1 over 4 times the coefficient. And the coefficient is 1 over 20. If I clean that up, what does that work out to be? 5, all right? Now, am I done? Is that my answer? 5. No, the question says what are the coordinates of the focus? So where is the focus x and y stuff? Yeah, it's at 0 because it's directly above the vertex, and 5 because that's how far I was told to get to the vertex, the focus. You with me? Okay. Is that all for problems? All right. Let's go determinants. Phew. Especially matrices are way more important now in the age of computers than they used to be. But it is often the case that the algebra problem is always the same. What makes one different from the other is just the numbers. And so some genius along the line said, you know what, let's just strip the x's and y's and all that stuff off and strip it all the way down to just the coefficients. That's where matrices come from. And man, lots of good stuff. You're going to do a ton of matrix work in second semester, a little bit in first semester. So, do you remember how to find a determinant? Yeah, you multiply down. Think of it as birds fly from Oregon down to, I was thinking Florida, but okay, Mexico. Technically, isn't Mexico straight down, so I don't want you to multiply straight down. Think Oregon to Florida, okay? So, Oregon to Florida, you multiply down to the right and subtract up to the left, which I guess would be Baja to Maine or whatever. I don't know. You work it out. But at any rate, that's the process. You multiply down to the right, subtract up to the right. So with that, what is the determinant of number 3? Negative 1 times 5 minus 3 times 2 is negative 5 minus 6, or negative 11. Now, 2 by 2s are super duper easy. You have to be a real goofball to miss a 2 by 2. Now, 3 by 3s, they're much harder. Well, do you know? Have you done 3 by 3 matrices? Yeah. Oh, you have. Have you? Regular? Oh, okay, I can't remember. Sorry, I have a hard time remembering in the green book where stuff is. Okay, we'll do 3 by 3s this year. So, with that said, number 4. Gosh, this is weird. First of all, there's x's in there, and they tell me what it equals already. What the heck? Well, let's still do the same process. Oregon to Florida means we multiply x plus 4 times x plus 2. And we subtract 5 times 3. And it equals, they're telling us what it equals 9, all right? So we do the determinant, and they say it equals 9. Now, because they tell me what it equals, that allows me to figure out what this is. X squared plus 6x plus 8 minus 15 equals 9. How would you solve that from here? Get all the x's on one side, the numbers on the other, or everything on one side? Everything on one side. And when you get everything on one side, you get something like negative 16. If I did that right. Do you all agree? Okay. Does that factor? Does everything factor? Not cleanly, but this does factor cleanly. What are the factors of 16 that, negative 16 that add to positive 6? Positive 8 and negative 2. Therefore, my x solutions are negative 8 and 2. Is there any reason I can't have negative 8 or 2? Is this like a log question where you could have negative? No, you can have whatever kind of solutions you want. So they're both good to go. All right? Questions on determinants of matrices? Cool. All right. Polar conversions. Oy, oy, oy. That's definitely after review. We don't do a lot of imaginary calculus, but it's all coming back to me now. So when you go to polar, They give you all these equations. They said this, you will remember this. Do you remember all this? Alrighty then. Well, here he goes. Could you draw yourself a graph? Draw a complex plane. Did you know that there's like a, you know, like in, did you see the Spider-Man and the Spider-Verse and all that stuff? Megan? Did you see that? Oh, that's too bad. Okay, well, there's like this alternate reality, all right? So behind the normal XY graph plane, beneath it there's this hidden graph plane called the complex plane, where the horizontal is the real component and the vertical is the imaginary component. So if I wanted to graph 2 plus 3i, that means go 2 to the right in the real and 3 up in the imaginary, and there is the point 2, 3 on the complex or real imaginary mixture plane. You follow? All right, and that's called taxicab geometry. If I wanted to get there, I could follow the streets basically. Go this way, north, east, west, and this way, north, south, and I get there. Couldn't you also get to that point in space by, if you were a bird, couldn't you just turn in that direction and fly oh so far? Are you with me? Now in that case, the bird would need, all right, what angle do I turn? And how far do I travel? That's r and theta. Now I could get directions then on a coordinate plane 2 different ways, rectangular or polar. This here, this is rectangular, and they sometimes want you to convert to polar. Gosh, I am not big on memorizing. I would rather you do this conceptually. So I am going to ignore these up here, and if you like to memorize meaningless stuff you don't understand, go for it. But I'm going to actually do this with meaning here. So if I were to graph this on the complex plane, how do I get there? 6 to the right and down 2. That's that point in polar. You follow? Okay. Now then, I could get to that point in space also by finding how far do I go and the angle I turn. Now what do you want to do first? What do you think you could do first? Do the r or the theta? Theta? Theta's harder, but okay, let's go for it. How do you find theta given that you have opposite and adjacent? Tangent. Wow, you sound so clever. Tangent is negative 2 over 6, yay? Theta then is the inverse tangent of negative 2 over 6. And so with a calculator, let's go something like, oh man, my calculator's always doing amazing. I want this, probably want to, you guys probably want to work in degrees, don't you? Do you remember how this green book did their answers in degrees? Anybody know? You're the teacher, man. What is this? Let me go in degrees, sorry. Document settings. You might want to get a calculator. Alright, here we go. Inverse tangent. Of negative 2, 6. I get negative 18.434 degrees. That makes sense. My graph is not to scale. Negative 18.434 degrees. Are we cool? All right. How do you find the r? Look at that now in a geometry sense. Pythagorean theorem. Write yourself a note. R by Pythagorean theorem. That's what this part is saying. By Pythagorean theorem, r is the square root of 6 squared plus, technically it's negative 2, but it's being squared, so I'm not going to even sweat the negative if you don't mind. R is the square root of 40, which is 2 10. So in polar form, this is 2 root 10 cosine, I sine. Oh goodness, we haven't even talked about that. This is just a mess. 2 root 10 cosine I sine 18.434 degrees. Would you read that as, or write in your notes, this is spoken as cosine I sine? You might ask, is it okay if we just say cis? And the answer is no, no, 100,000 times no. It's not okay. You might as well just go around grunting like some kind of uncivilized caveman. If you're going to be an intelligent person, say it. Cosine I sine. Yes?
Does it matter that the area came out to be negative?
It does not. It doesn't to me anyway. Does it matter in the book? That answer is accurate. When you get a different quadrant, you're going to have to do some thinking. We'll talk about, I hope that's not tonight's homework because we'll have to talk about that. Yes? Oh, so great question. That's wonderful. You see there's connections between this. So awesome that you said that. All right. So you'll think, well, didn't we do this with this thing? And you're 100% right. You did stuff like this in Algebra 2 with this angle sign. The difference is that this is for vectors, and they're real. And this is imaginary. The principles are 100% the same, though. This is horizontal, vertical. And so it kind of matches the 6 minus 2i kind of thing, which is horizontal, vertical. And this is polar. What angle I turn and how far I go. The difference is that this is for real numbers. There's no imaginary to this thing. And so it is a lot of the same work, but when you're dealing with imaginary numbers, it's these two notations, not those two. Okay, so awesome that you made that connection. That's great. Let's go to 6, shall we? The best way to do this is to know what this stands for. I don't even need to draw this, quite frankly. This stands for 5 cosine negative 3 pi over 4 plus 5i sine negative 3 pi over 4. You don't even have to write that out, but that's why you say it, so you know what the heck that means, sis. What are you talking about? If you say it, you'll know what it means. This means take 5 times the cosine of negative 3 pi over 4 and 5 times I times the sine of negative 3 pi over 4. What is the, you agree, negative 3 pi over 4 is going down and puts you into the third quadrant. What's the cosine there? Is it, what's pi over 4's cosine? Is it root 2 over 2 or root 3 over 2 or 1/2? Root 2 over 2. And what's the sine in that quadrant? So this is 5 times negative root 2 over 2, and 5i times, what's the sine in that quadrant? Negative root 2 over 2. That's pretty much done. I guess cleaned up, it would be negative 5 root 2 over 2 minus 5 root 2 over 2 I. Say it again. Isn't it? But it's negative 3 pi over 4. Yeah, if they're positive, it would be positive. That's fine. Okay, are we cool? All right, that's going to take some practice. I feel like maybe that's a little iffy. There is a shortcut for multiplying two things in polar complex form. Do you remember this shortcut when you multiplied two things in polar complex form? What the shortcut is? Okay, the idea is that the first numbers you multiply and the angles you add. That's where they're coming from. This is multiplying and this is adding. This goes antithetical to everything I do as a teacher. This is just mindless symbol pushing. You have no freaking idea what you're doing, if it has any purpose whatsoever, which it does. But for now, we'll go with it, and I'll get to the purpose later. Please trust me, there is a reason you're doing all this symbol pushing. When you multiply these two together, so the numbers out front, we multiply, and we get 12. We don't say cis, because that'll make your teacher nuts. Instead, you say cosine I sine, and the angles you don't multiply, you add, and that is 420, that's unfortunate. Cosine I sine, let's go with, I don't know if the book would keep it as 420, just not because of 420, but because it's more than 360. I feel like they would probably call it 12 cosine I sine 60. If it's beyond 360, you should take it down as rotation. You with me? Okay, cool. I don't know if we have time to do 10 and 20 together. Do we have time? Do we have your book? Yes, ma'am.
Since it asks for a rectangular form, we have to keep going.
Oh, yes, this is polar form. Gosh, this is polar form. Now we need to go to rectangular form. Thank you. Excellent call. So we just talked about this, but it's brand new. You get this to rectangular by thinking expansion. It's 12 cosine 60 plus 12 I sine 60. And then you do the trig. What's cosine 60? 1/2. And what's sine 60? 3/2. And so this product in rectangular form, great call, is 6 plus 6√3 I. That's rectangular. Polar is the one with the angle. All right. Thank you, Leo. Excellent. All right. We don't have time to hit 10 and 20. It is what it is. Okay. So you need to either bring your book home tonight or take a picture of your book. It's not all of set 69. I think it's just 1 through 20. Did you guys just do about 20 last year? 15? I don't know.
We did 15. Well, we did 15 at the next
Semester. That or no, it'll be 20. That's a real. All right. I am sorry I did not anticipate going this long. We'll go over the test tomorrow, I guess. Oh. Oh, thank you. I actually had it in my hands all the time. Way to go, not getting double sets later. Oh. Okay. Have a great day, people. Thank you. Have a wonderful day.